All right, so what's the difference between a scalar and a vector quantity? So in the last lecture, we talked about vector quantities. Vector quantities are quantities that have both a magnitude and a direction, whereas a scalar quantity only has a magnitude. So I'm just going to fill that in here. A scalar quantity is one which only has a magnitude, whereas vector quantities have a magnitude and a direction. All right, so we're going to classify each of the quantities in the table below as either a scalar or a vector, and we'll give an example for each. So for example, the first quantity is distance. Okay, so distance is how far you're traveling. So let's say the distance from my house to the school is 20 kilometers. 20 kilometers. All right, so this is the magnitude over here. There is no direction. I didn't say which direction I have to go to get to the university. I just gave you the distance between my house and the university. So this would be a scalar. So I'll just write S for scalar. All right, speed. So let's say I'm driving, on average, my speed to get to work is 60 kilometers per hour. That's my speed. Again, there is no direction here, so that means that speed is a scalar quantity. Okay, then we have time. So time just means how much time does it take to do something. So for example, it takes me 20 minutes to get to work. Okay, so then if it takes me 20 minutes to get to work, then there's no direction involved there at all. So that would be, again, a scalar quantity. Okay, then we move on to displacement. So displacement is much like distance, except you have to give basically the distance it takes to get somewhere, but also including the direction. So for me to get to work every day, for example, let's pretend I'm driving 20 kilometers. But I'm traveling south. Okay, so my displacement is 20 kilometers south. So that would be then a vector because it includes both a magnitude and a direction. So this would be a vector quantity. Velocity. So again, velocity is much the same as speed. It just means how fast you're going, but you're also giving a direction. Now, direction can be south, east, northwest. It could be east 30 degrees north, for example, but it could also be up or forward or backward or down. Okay, so there's a lot of different examples of directions. It could be also 30 degrees above the x-axis, the positive x-axis. So these are all examples of directions. So let's say my velocity when I'm driving up to the cottage is on average 100 kilometers per hour, and we're traveling north. Okay, so that would be my velocity, and that is a vector because there is both a magnitude and a direction. Okay, so that's a velocity. Acceleration. So acceleration is how fast your speed or your velocity is changing over time. Okay, so let's say you are parked in your car, and so your velocity at that moment is 0 kilometers per hour, but then after 1 second you've accelerated and you're now traveling 5 kilometers per hour. So in 1 second, your car sped from 0 kilometers per hour to 5 kilometers per hour. That would mean that your acceleration is 5 kilometers per hour per second. Okay, so in 1 second, you accelerated, or your speed changed by 5 kilometers per hour. Now, if you're traveling north and your speed is increasing, then your acceleration would also be north. All right, so acceleration is a vector. You should be including both the magnitude and the direction. So acceleration is a vector. Okay, if we were to talk about SI units for all of these things, the examples that I've been giving are not in SI units, right? So for each of these, if I were to put in the SI units, for distance, the SI units are meters. For speed, meters per second. For time, seconds. For displacement, meters. And then a direction. I'll just write dir for direction. Velocity, meters per second, and then a direction. And acceleration, the SI units are meters per second squared, and then a direction. Okay? All right, mass. So mass is, for example, my mass might be something like 75 kilograms. Okay, the SI unit for mass is kilograms. Force. All right, so this would be like a force that's acting on an object. Let's say the force acting on an object is 30 newtons. Okay, so if we go back to mass, does that 75 kilograms have a direction to it? It doesn't. It's just a mass. This is just how much something, like the amount of mass is in something. It doesn't have a direction to it, so it is just a scalar value, no direction. But a force actually does have a direction. It points in a certain way. So forces are vector quantities. So let's say 30 newtons down would be an example of a force acting on something. So I pull on something downwards, there's a force acting on it of 30 newtons down. Okay, so newtons is the unit, the SI unit for force, and you have to give a direction. So because force has both a magnitude and a direction, it is a vector. All right, and then we have energy. So I had a bowl of cereal this morning. It was 200 calories of cereal and milk. That's energy. There's no direction to it. Okay, the SI unit for energy is the joule. No direction, so it is a scalar. All right, so I hope that all made sense. It's really important that you can distinguish between scalar and vector quantities, because if, for example, I ask you for distance, I only want the magnitude. But if I asked you for displacement, okay, distance and displacement are very similar. They're both measured in meters in SI units, but displacement, I expect you to give a direction. Likewise for velocity, for acceleration, and for force. Okay, so make sure you're including directions for those vector quantities. All right, so now we're going to introduce the 3 kinematic equations that we're going to be using throughout this course. And these equations are provided for you on your tests and exams, so you don't have to memorize any of them. The equations are only valid when acceleration is constant. All right, so if the acceleration is not constant in a question, you can't use these equations. So in this course, anytime you have to use one of these equations, we're assuming acceleration is constant. Okay, so we have a bunch of different terms or variables in these equations, and I just want to make sure that you understand what each of them are. So let's start off with SI. Okay, so SI is over here. All right, so SI means the initial position. So an object's initial position. Okay, so the S is position, and the I stands for initial. All right, next, SF. SF. So what do you think that stands for? Instead of an I, it's an F, so it's final. Final position. And you'll see SF in the first equation there. All right, next we have delta S. Delta S, so delta S, you see it over here. Oops. All right, so what does delta S? Well, the delta, which is this triangle over here, stands for change in. Change in. And the S is position. So delta S is the change in position. So if you were to think of a ruler, And let's say we're at the 1 centimeter mark here, 2 centimeter, 3 centimeter, 4 centimeter, 5, 6. Let's say this is 7, and it keeps going. Let's say we started off over here. That would be my S initial, which is 2 centimeters. And let's say I finished off somewhere over here. So let's say that would be my SF, then my final position is 7 centimeters. So then my change in position, what would that be? It's the distance that I've traveled, the change. So I went from 2 centimeters to 7 centimeters. So my delta S is always equal to S final minus S initial. So 7 minus 2, which is 5 centimeters. So that's the distance that I traveled right here. That's my delta S. Okay, so delta S is the change in the position. How far did you actually travel? Okay, now let's move on to V. V initial. So V over here, V initial, we see it again over here, and we see it again over here. Okay, so V stands for velocity and I for initial. So this would be initial velocity. Okay, then we have V final. So V final, VF, V again for velocity, and then F for final. So we have final velocity. All right, now we have acceleration. So here's acceleration right here, here, here. Notice acceleration is in every equation. So in order to solve any kinematics problem using any of these equations, you need to know the acceleration. All right, so the acceleration, that's all that is. I'll just highlight it so it corresponds. And then finally, we have delta t. Delta t. So you have delta t here, and we have delta t here. We have delta t here. Okay, so two of the equations have delta t in it. What does delta stand for? We already said before that little triangle means change in, and then t is time. So delta t is change in time. All right, so there's my delta t. Okay, so what that means is, let's say my initial time, so let's say I'm running a race and I start the race at 5:15 p.m. and I get to the end of the race, so that would be my initial time, t initial. I get to the finish line at 5:23 p.m. Okay, so that was my initial time, my final time. My change in time is when I subtract the two. 5:23 minus 5:15, so that's 8 minutes. So delta t, the amount of time that went by from when I started to when I finished, is 8 minutes. Okay. All right, so let's practice using these equations on the following word problems. Okay, so we have an airplane that's accelerating from rest down a runway at 3.2 meters per second squared. So before we continue, let's identify what that variable is, 3.20 meters per second squared. Okay, actually what we could do is we can go through all the variables we discussed above, and let's write the SI units for all of them. So position, SI unit would be meters, final position still meters, and change in position still meters. They're similar to distance. V initial, so that's our speed or our velocity, meters per second. V final, still meters per second. And now acceleration, meters per second squared, and time is just in seconds. It's really important that you know what the units are for each of these, because sometimes in a question, it won't tell you what the variable is representing, but you can figure it out by looking at the units. So when we look at question 2 and it tells us the airplane accelerates from rest down a runway at 3.2 meters per second squared, well, we can identify those units as being the units for acceleration. So that is our acceleration. For 32.8 seconds. Okay, that's the amount of time that's gone by. So that is our change in time, delta t. 32.8 seconds until it finally lifts off the ground. Okay. Determine the distance traveled before takeoff. This should say it. The distance traveled before takeoff. So this is how far it's traveled. It's not the initial position. It's not the final position. It's the change in position. It's how far it's traveled. Just like in this ruler example, we started off at 2 centimeters, we finished at 7, but the distance traveled is 5 centimeters. So we're looking for delta S. That's our question mark. That's what we're looking for. Okay, so the next thing that we're going to do is identify which equation we're going to use to solve this problem. We are looking for delta S, we know A, we know delta T. Okay, so let's take a look at our 3 kinematic equations and identify which one is it that we want to use. Okay, delta S, delta T, and we're looking for, and A. So we want an equation that has A, delta T, and delta S in it. Now, one thing before we continue, this first equation, it's going to be given to you the way you see it here, SF equals SI plus VI delta T plus 1/2 A delta T squared on your tests and on your exam. But you can recognize that if you were to bring this SI to the left side of the equal sign, the equation can be written as SF minus SI, because remember, when you move something to the opposite side of the equal sign, it changes its sign, equals V initial delta T plus 1/2 A delta T squared. Now, what is SF minus SI? It's equal to delta S. So that equation is the same as delta S equals V initial delta T plus 1/2 A delta T squared. Okay, so keep that in mind when you're doing problems. If we look at this question does not have anything to do with V in it. Oh, actually, there is one thing we missed. Let's see if you can find it. It says an airplane accelerates from rest. So that is actually giving us a piece of information that we had missed. What information is that? It's telling us that the airplane starts at rest. So what does that mean? It's resting, it's not moving yet. So its initial velocity is 0. V initial equals 0. And I'll put in the units, meters per second. Okay, so that's actually something that's really important to keep in mind. Sometimes it seems like you don't have enough information in a question, but there's sometimes terms like that from rest that gives you more information, but it's not so explicit. Okay, so now we have an extra variable. What is the one variable here in these 3 equations that you don't see listed in over here in question 1? A, delta T, delta S, and V initial. Which variable is missing? It's actually V final. V final is the one variable that we don't know and we don't want to know. It's not asking us to find it. So this is the variable that we don't want to have in our equation. So the way that I identify which equation to use is I identify which variable we don't have and that we don't want to know, and I find the equation that doesn't have that variable in it. So which equation would that be? Well, equation 2 and 3 both have V final. Equation 1 doesn't, so it's equation 1 that we're going to use. Okay, and remember there were 2 forms of equation 1. There was SF equals SI plus VI delta T plus 1/2 A delta T squared. But if you bring the SI to the other side of the equal sign, that becomes delta S equals V initial delta T plus 1/2 A delta T squared. So you have to figure out which of those two equations do you want to use. Well, we're looking for delta S, so let's use the one that we created here on the left side. So I'm going to rewrite it. It looks like delta S equals V initial delta T plus 1/2 A delta T squared. All right, delta S is what we're looking for, so it's great. It's already isolated on the left side, so we don't need to rearrange this equation at all. We're just going to leave it the way it is. V initial is 0. I'm subbing in the values that I know in brackets. Delta T is 32.8 plus 1/2. A is 3.20, and then delta T again is 32.8 squared. Okay, notice that the units that were given in the question were all SI units, so I didn't need to convert anything. Now I'm just going to type everything on my calculator. 0 times 32.8 plus 1/2 times 3.20 times 32.8 squared. And I get delta S is equal to 1721.3. And my units, delta S, is the distance traveled, so it would be meters. Okay, the question's asking for distance. Distance is a scalar quantity. I don't need to include a direction. And that's it. That was question 2. So I should change that. That should say question 2. All right. So let's move on to question 3. A girl is running across a track. The girl accelerates at 6.00 meters per second squared. So let's write what that is. It's the acceleration. You can tell because it says she accelerates at that acceleration. It also gives us the units meters per second squared, which are the units for acceleration. So I have acceleration is equal to 6.00 meters per second squared over a distance of 6.90 meters. So that would be my delta S. That's the distance traveled is 6.90 meters. When she reaches a speed of 24.8 meters per second. So she reaches that speed, that would be her final speed. So that would be V final is 24.8 meters per second. What was the girl's initial speed? So we're looking for her initial speed, V initial. That's our question mark. That's what we're looking for. So when you think of the kinematic equations, what is the one variable that is not here listed at all? We don't know it, and we don't care to know it. It's not asking us for it. It would be time, delta T. Change in time. That's the variable that we don't know and we don't want to know. So let's take a look at our 3 kinematic equations and look for the one that doesn't include time. Okay, so equations 1 and 2 both have time in there, but equation 3 doesn't. So that's the equation we're going to use. So let's do that. So equation 3 was V final squared equals V initial squared plus 2A delta S. All right, we're solving for V initial. So let's rearrange the formula so V initial is on its own. So that means we're going to take all of this and move it to the other side of the equal sign. So I have V final squared. Instead of it being plus 2A delta S, it's going to be minus 2A delta S is equal to V initial squared. Now we want to get rid of the squared, so all we have to do is plus or minus square root both sides. So I have the plus or minus square root of V final squared minus 2A delta S equals V initial squared. And I'm just going to rewrite it, so V initial squared. Sorry, it should just be V initial because I square rooted it. So now I'm going to just rearrange it. So V initial is on the left side. It just looks nicer that way. Equals plus or minus V final squared minus 2A delta S. Okay. I really recommend that you rearrange your equation to solve for the variable you're looking for first, rather than subbing in your numbers. But if you can't do this, or if you really don't like doing this, go ahead and sub in your numbers. As long as you're getting the correct answer, it's fine. Okay, so you wouldn't lose marks for that, but I just want to recommend that we do that, so I'll try doing that when I do these videos for you. All right, so now we're going to sub in everything that we know. V initial is equal to plus or minus the square root of V final, which was 24.8 squared, minus 2. The A value was 6.00, and delta S is 6.90. Notice that all the units given were SI units. I don't bother to include them in my equation at all. I just put the final answer with units. So now I'm just typing this on my calculator, the square root of 24.8 squared minus 2 times 6.00 times 6.90. And I get V initial is equal to plus or minus 23.07, and the units for that would be meters per second. All right, so now there is a plus or minus in front, and we have to decide which is the correct one. So the question's asking us for speed. Is speed a scalar or a vector? Speed is a scalar. So that means no direction. No direction. Plus and minus kind of indicates a direction. If you say positive, that means you're going in the positive direction, whichever way that you define that to be. Maybe it means forward, maybe it means east or north. And minus means the negative direction. But in this case, we don't care about the direction, so that means we don't care about the sign. You would never put in a negative for a speed, because that would indicate you're going in the negative direction. But speed, when we ask for speed, we're not looking for direction. So I'm just going to get rid of this altogether. My answer is just 23.07 meters per second. That's my V initial. All right, so that's the final answer. The girl's initial speed is 23.07 meters per second.